right. Thank you, everyone. Welcome. This is Open Research Institute's FPGA projects meetup and office hours for the 20th of May, 2025. And welcome to everybody. And what we do at this meeting is we talk about what we have done over the past week or so and what we have planned for the next week or so. If we need any resources that ORI can provide or obtain, and if we have any roadblocks, anything that's kind of blocking our way, anything we need help with, that's what we do. And so turn the floor over to Aaron and welcome and let us know how it's going.
Sure. So I don't have significant progress this week. My focus right now has been focusing on implementing or getting an implementation up of the DVB-S2 encoder that ORI has developed. So I'll continue working on that. And as far as resources, I think last week you mentioned if you can provide me some links to getting the Pluto SDR implementation up and running as a reference implementation that I can base it off in order to get OpenCPI running on it. That's all I have this
Okay,
week.
very good. Yeah, sorry for not closing the loop on that as quickly as I wanted. We've had a graduation here in the household, and so there was some travel, and that delayed things a lot more than I thought they would. So and also probably rely pretty heavily on Matthew and also F50EO to that the resources will definitely come from them. So I'll do a better job this week in putting you in touch with or getting you connected with the resources. Okay, so I'll turn the floor over to Matthew whenever he's able to take over and tell us how things are going and what he's got planned and needs any resources or has any roadblocks.
Spent a little time looking at the modulator still and just working through those issues, but I didn't have enough time to get through it entirely. So I'm hopeful that this next week I'll make more progress. And the other thing I had meant to do, and I'm sorry I hadn't yet, was make a proposal for the hardware level framer. So I'll hopefully look at that this week, assuming I have time and put that in Slack so we can talk about it. That's it, unless something comes up in the discussion.
Yeah, I think Aaron needs some particular help with the Pluto SDR implementation.
Okay.
I think that's an action item actually from last week. I'm not sure that I came through with enough resources or help over the past week due to travel that took a whole lot more out of me than I thought it would.
Aaron, if you could post whatever you need in Slack, and then I can
Sure.
look at it and see
Yeah.
what I can do to help.
Yeah, basically, I'm just trying to come up to speed with what's already been done as far as the DVB-S2 encoder is to get it transmitting. I think if it's just a video or something, just to test out, ring out where the encoder stands as it is today.
Oh, well, I mean, so for the MSK modem, we don't have a DVB-S2 encoder. It's just the MSK modulator, and it has a fairly simple differential encoder in front of it.
Yeah, I think it was not necessarily the MSK implementation, but just trying to get the overall system downlink is the DVB-S2 encoder.
Okay.
And I just wanted to get that up and running.
Okay, yeah, we'll definitely keep working on that. Yeah, Sawato was the original author on that, and I know that there's still a few action items to or things that he would like to see implemented into the encoder. So yeah, this would be the downlink for the MSK portion, and all of the opulent voice is the uplink part, and then we've been talking about the the process of like taking all these different uplinks and packing them into frames, and then presenting them to the downlink encoder for the DVB-S2 S2X work. So yeah, this is super exciting. And yeah, we need to start going ahead and connecting the dots there and making sure that you have everything that you need. So the published work is all VHDL. So that's a an implementation that we know has gotten some exercise and some use in a couple of different ways. Um, but there's a lot of rough edges with it. So I think that the support is definitely owed, and we should be paying a lot more attention to that and helping out. So let's see what we can do over the next week. I know that we'll probably need Paul here and loop in both Evereast, who's done an implementation on the Pluto for this particular modem, and also if Swato has any time to answer any questions if we need. And looking at the list of outstanding things to do on this particular part of the design, there are some things that would help to further improve the quality. It does work and delivers, does its job, but there's still things that could be done on that particular design. So thank you so much, Aaron, for being patient with us over the past week, and we'll put our backs into it over the next week.
Thank you.
You bet. All right, Matthew, back to you.
All right, I didn't really have anything else this week, so if something comes up, I'll jump in.
Okay. Uh, do you want to outline you have a suspected bug? Did you want to like just in broad terms kind of
Oh,
like
sure.
define what that's about and what you've seen, what you can just
Sure. Well, I mean, last time we were in the lab and we were going through some of the testing that Paul had set up, and there was an anomaly, and I'm trying to. It's been several weeks, so I can't quite remember the anomaly, but basically, there was some bit error issue, if I remember correctly. And so I had gone back in and double checked the code and realized that the differential encoder that I had implemented wasn't the one I had intended to implement. So I intended to implement the Massey encoder. It wasn't, but it wasn't right. And so I fixed the encoder, and then we stopped decoding properly on the receiver. And it wasn't clear to me quite what the problem was. And in doing further review, what was really odd was um, if I left the sync sequence in during the simulation, after the sync sequence was completed, the decoder was only decoding the F1 symbols, and it was attributing everything to F1, and there were no F2s. So the F2 frequencies, the F1 and F2 frequencies, right? So everything was being decoded as F1, and F2 was never being decoded. It was like the decoder thought there was only F1 symbols being sent and no F2 symbols. And so that was really weird. And then so I dug through it some more and realized I didn't really want to do the Massey encoder. I wanted to do the I'm gonna butcher his name, I'm sorry, Schoons, from the Schoons Hodgart paper. And so I re-implemented that, and the now I after some machination. So there were, I think, some decoding alignment issues. So there's pipeline registers in the decoder, and I don't think they were aligned properly. So I'd spent some time on that and cleaned that up. And so now the decoder is decoding the way I would expect in terms of it's getting F1 values and F2 values and the but it's not clear to me that the loops are locking yet, and certainly I'm taking bit errors. So it's not like over some period of time everything locks good and the bit errors go to zero. So there's still something broken in the decoder, or at least I'm pretty sure it's in the decoder. So I view this more as a on optimization and kind of a technical debt removal, although, there can't be that much in this design, um, but just, cleaning up the code and trying to address, simplifications that I may have made during the development process. And so I think that's all it is. It's just some cleanup and making some things right. And then hopefully those anomalies, the expectation is once I get this done, that the anomalies that we were seeing in the lab testing, would be resolved. And I don't know if Paul remembers what those anomalies were, but there was something not quite right. And in general, there was still some funniness with the design. I think we still saw the split spectrum on occasion. And so I'm thinking that maybe that's still related to the encoder, um, to the previous encoder. So I'm hoping that this effort will result in, more robust and stable operation.
Yeah, the split spectrum, which was quite artistic, very interesting effect that we saw on the spectrum display. Yeah, it returned unexpectedly because we thought we had eliminated it, and we thought we understood why. So
Right.
yeah,
Right.
this is a rich, fertile ground for learning and improving things. But it sounds like that's a lot of progress that you described, and thank you so much for battling through very difficult work to get a very worthy design.
Well, I'm happy to do it, but on the other hand, I put the errors there, so um
Understand.
but yeah, the goal is to get this functional and working and have something that's, robust with the Plutos and that we can start building on, for the opulent voice layers on top of it and have something that, like I said, robust and is working well.
Yeah. Well, lots of huge steps forward over the past month or two for sure, and it sounds like over the past week there's been a tremendous amount of work. So we all deeply appreciate it, and looking forward to next cut of code. Um, so as soon as you have something that you are comfortable testing in the lab, then um, just let us know, and
Yep,
we'll do
and
it.
do that for sure.
Awesome. Yeah, thank you. All right. Let's see. Thomas, welcome. And you have the floor. Anything you want to share, talk about, or that we need to know about? Any resources that you need, or anything that we can do to kind of move either the link budget work or the plans for 2026 forward?
Yes, thank you. So the resource I need is time, but I'm not sure if you can help with that.
Yeah.
No, that's
Standing order.
actually I have been catching up on the previous meetings that I missed, and really nice to see the progress on the Venus budget, also incorporating some of Daniel's work, which is of course excellent. That was a real nice to read as well. My goal, and I hope to be able to show that next week, is to actually put all the numbers we have from the successful Venus bounce in a very simple link budget, just as something to keep next to your big Jupyter book, so you can actually check some numbers, see if they match or not, and as a kind of verification. I mean, we have one data point, so that's still on my to-do list to come up with it.
Awesome. Yeah, that would be super, super helpful. Because yeah, all the different the research and the analysis and all of the details that we have absolutely have to um, comply with and take direction from real world results. And there's a ton that we can learn from the data that you all have, and we are in the process of doing this with the previously released the IQ data and the existing stuff that exists. But yes, thank you so much. We really want to make our analysis and the book accurate, and the only way to do that is to be completely oriented and focused on real world results from actual equipment. And and actual events. So definitely looking forward to that. Thank you.
The other data point we have, of course, is from the Bochum bounce from 2009. But there you have a few unknowns in the link budget. They had RFI and things like that, which makes it much harder to properly estimate. But still, it's also useful.
Correct. Yeah, they did have some challenges, and there has been some updates over the past couple of months. They published a lot more from the 2009
Yes.
experiment. And yeah, they did. They had there's an article that went into detail about the particular RFI challenge, local RFI challenges that they had. Yeah, good point.
And if I may, I actually have one question. I saw on the website the proposal for DSAS to measure the surface of the dish.
Yes.
Which is really interesting. I had never heard about that. So do I understand correctly? You just make photographs and you have software to actually reconstruct the mesh or the form just from the photos?
Correct. It's a photogrammetry method of getting a surface, an accurate surface. And what you do is you distribute some sort of marker, and there's a variety of markers that you can use. You can use particular tags or codes so that each marker is a individually recognizable object like a QR code or barcode or something like that. Or you can use something just like a reflective color to where you can then tell your software to look for these colors. And as long as you take enough photos from different directions, and as long as you have a few firm references, a few known, like the distance from your particular photograph from your eye or from the focal point out to that particular point, this identified point, as long as you have some anchor points or some reference points, then you can derive or calculate a mesh surface, some sort of, so you have a collection of points, and then you can connect them with triangles and make a mesh, and then you can close the mesh with some software. So then now you have an actual surface. So you do have to take a fair number of photographs doing this in a photographic way. Another way is to do this all with LiDAR. But photographs, camera, in order to keep this inexpensive, then you're just spending time moving your camera around and taking photographs of a surface that you covered enough with these tags. Then that's a known good way to get surfaces. This is used mostly in like archaeology or in civil engineering or with like bridges and things like that, where you have to determine like, is the bridge going to fail because it's deflected beyond its limits, that sort of thing. So that's where it comes from. It has been used with a couple of dishes, especially ones that have been salvaged, to determine whether or not the dish is still within the RMS limits of the reflective surface. So that was our recommendation because they didn't have a lot of money and it can be done in a weekend if you're organized. So that was our recommendation to DSES because they don't have a good evaluation of the dish surface. They don't know how good it is, and they have about a 20 dB difference that they're trying to figure out why the dish is 20 dB, 18 to 20 dB down from where it should be.
That's huge. Wow.
It is. It's really big, and they're seeing this. It's consistent, and it may explain why the results from March 2025 were not as good as they hoped. And if we can get this won't like solve all problems, but getting the RMS, deviation from parabola, which is, for the Ruse equation for TSIS, this will settle a lot of issues. You now know, like, is the dish a different shape than you assumed? Or is the dish deformed beyond, the 3 millimeter that it was 3 or 4 millimeters that these particular dishes were designed to
Yeah.
fly with. The actual specification for this dish, it's supposed to only deflect up to 6 millimeters RMS in 100-mile-per-hour winds. And, because they're military dishes, military radar dishes. And the rule of thumb for a dish of this particular size and this particular provenance, this military radar dish, is that you can assume like 1.5 to 3.0 millimeter RMS. But this is a really old dish that's been out in the weather in Colorado for a long time. It could be really bent up and beat up. It might not look like it, but your eyeballs can't really tell.
No.
So this method should clear up the actual surface of the dish. We should be able to get a decent mesh in software and then look at it like, okay, this is what it was supposed to be, supposed to look like. Here's what it looks like now. And that may result in some number, maybe a large number of dB difference from ideal. So that was our answer to the question that they posed to us of how the heck do we measure what our dish really looks like today. And that was the cheapest, quickest way that we could come up with to advise them to measure it.
Well, very interesting. I had not imagined you could do that so accurately with just photographs, because if you want to measure an RMS of 1.5 millimeter, your reconstruction of the dish needs to be even a factor more accurate than that.
Correct. You can do
That's
it
amazing.
with enough photographs. And I think for a dish of the size of DSES, then you're going to need at least 100 different photographs from various angles.
Yeah.
And like we talked with them in person, and it's like, well, and also depending on where it's pointed, if it's pointed straight up versus if it's pointed at 0 degrees, then maybe at this point the dish is sagging a little bit or changing a little bit. You don't want it to, but you also have to think about that. So pick an angle that you are going to use it. Like you want to use it for Venus, then 45 degrees, 30 to 45 degrees is probably where you want it. And then measure it there and see how it looks. And, but you'll need at least 100 photographs with a pretty high end, a decent camera to get enough resolution. And yeah, you can derive a mesh surface of the dish doing this, and it will be accurate enough to give you good results.
Yeah.
You do have to take enough photographs. You have to have enough of these little tags.
What is the order of number of tags you would need for a dish like this?
I worked it out, and you're gonna want like at least every meter or so, and you definitely want to include tags on things like struts. Anything that's kind of in the way, you want to include those if you're going to go on and then use this mesh surface in like the in the software that actually includes that. So there's RF analysis software that will include struts and structures, local structures, and But basically, as long as you just get the surface of the dish, you'll be able to use the Ruse equation to see the damage done in the system temperature, and that will definitely, it may not explain all of the discrepancies that they're seeing in their link budgets.
Yeah.
Like they're seeing performance loss of quite a few dB, like up to 20. But it will, if there is some surface irregularities or, as long as they know, as long as you can put it in there and you can see what you can do. You can still use the dish for a lot of different things. And then, if you know that your dish is actually a different shape than what you thought, then you can move, for instance, you can move your phase center. You can move the feed like, oh, this isn't like we're out of focus. And then you can figure it out. You can move it. Another thing that they're going to do is put some mirrors down and actually confirm the phase center visually with some mirrors and figure out if it's out of focus or not. It doesn't have to be off by much to really lose a lot on a dish like this. So
yeah, actually, that's the so on the surface, I fully agree. On the focus, it's remarkable forgiving. the focus point.
Oh, that's interesting.
Yeah,
Yeah,
so
on smaller
we
dishes,
actually have a motor on the focus, so we can move the focus over almost half a
right?
meter, and you really need to move it a lot before you start seeing significant loss. That's amazing. Yeah,
Okay, yeah, on a smaller dish, it's not very forgiving, but I can see where a larger
true.
dish it would be. So, I think that they're going to move forward with this and to figure it out to measure it, because it hasn't been, um, and they don't really have good blueprints, which is, I guess, not really surprising given the age of the dish. They don't really have good design specifications for this dish. They're just looking at it and kind of like taking a laser level and guessing and looking at the original contract, for the radar dish. And if this helps, I think it will
Yeah,
definitely help one way or the other. It's if it if
yeah, it's really it's really interesting. I would almost be tempted to try it out, but getting a tag on the telescope every 1 meter is not really easy. We can't access the surface of the dish easily.
Yeah, I think the DSES people are totally okay with like tromping around on their they walk around and get up there all the time. So I knew that this suggestion, this would work out for them. But, it's yeah, no, I'm looking forward to hearing the results. And that will make the data class that we have more accurate. It will definitely let us fill in the parts of the system temperature that depend on,
Yeah,
quantifying the RMS, irregularities of the dish. They'll
yeah.
at least clear that part up, and that's actually a really big influence on the rest of the link budget. So, and
Yeah, it does. And if they already knew they had 20 dB loss somewhere, they could have saved themselves a lot of trouble trying to transmit
yeah.
to Venus, I'm afraid.
Yeah, I think that there was a
Anyway,
lot of optimism and the discrepancy that Alex, um, the person that's most interested in figuring this out, Alex K6 VHF, and he was like, he gets it, and he's like, he's seeing this discrepancy and the the results from their astro side, from the radar astronomy, or the astronomy side, the
mhm.
sciences side, they don't really see this as a big problem because the work that they're doing isn't dependent on the link budget. They can achieve their goals with this loss. They're seeing the results. It's either there or not, like these hydrogen lines or deep space objects that they're looking at, they're either seeing them or not. Now they are seeing like less energy than they expected, but once they see the result, since it's a sort of a binary, yes, we've spotted it or we haven't spotted it, they're less sensitive to this issue than the communications side of DSES, which is the ham radio
Okay,
on the communication side. So, especially with Earth, Venus, Earth, this is a really difficult link budget. So, 20 dB actually makes, 12 to 20 dB is a huge amount of loss to kind of, figuring out where it is. So Alex found a big problem with the feed line, replaced the feed line. That brought things up, but it was only part of the problem. And he's still seeing this, still a significant deficit. And, now it's like, well, if you don't know the dish surface and you don't know exactly what it looks like, then, that could be a problem. So we're just knocking down
yeah,
one problem after another. And
yeah,
eventually we'll find the root cause and eliminate it.
yeah. Okay. And by the way, I do think for astronomy, you have exactly the same issue. You might indeed still see the bright objects, but ultimately it defines on how far you can look. I mean, we're doing
Yes.
measurements that take 1 or 2 hours of integration.
Right.
So they're actually weaker than what we did with Venus.
That is
So
true.
yeah,
That's you are exactly right. I think the reason that the science side of DSES probably hasn't flagged this is because they're still working through kind of a backlog of here's
sure.
all the big targets that we're expected to see, and they're now they're now good. They're going to run into this very, very soon if they haven't already, with more and more difficult targets and moving more towards the let's do some actual science rather than confirming confirming previous results because
Yeah.
they're still kind of working through, I guess, the big ticket items, all the things that you're expected to be able to do is in this area. When they start looking for harder stuff, then yes, this will this will
Yeah.
be right on their doorstep too. This will directly affect the ability of the dish to do things. And they are kind of like moving in that direction. And hence, we the two sides essentially of the site, because there are two distinct communities at DSES. They're now their needs are are now the same. They are running into the same problem. So you're exactly right. Yeah, right on target.
Okay, well, thanks for the explanation.
Uh,
It will be
uh,
interesting to see the results of this.
Very much so.